Good morning students. Class 12th, chapter number 5, summary of the chapter Continuity and Differentiability, lecture number 15. Today I am going to discuss all the concepts in brief as we have already done everything in detail. So let us revise the topics. The first one is continuity of functions. In continuity of the functions, we need to check whether the function is continuous or not, and we know the conditions of continuity, that left hand limit, right hand limit, and the value of the function at that particular point should be equal. Let us take one example here. Look carefully. The function is given for different values of x. The function's value are different. So here there will be 5 cases. The question will ask you to check the continuity or to tell the points of discontinuity of the function. So you have to check at x less than -3. The second case will be you will be checking at x equals -3. The third case will be you will be checking at x lies between -3 to 3. The fourth case will be x equals 3, and the fifth case will be x greater than 3. So these will be the 5 cases on which you have to check the continuity of the function. Now suppose we are checking for less than -3. For less than -3, the function value is modulus of x plus 3. We see it is a polynomial function, hence it will be a continuous one, right? So directly we can say. Second case, when we check for -3, let us check f of -3. So for equal to -3, you observe we will take modulus of x plus 3 as the function. In modulus you will write -3 plus 3, so the answer will be 6. Then you will check for limit x tending to -3 minus, which is LHL. So for less than -3, the function is modulus of x plus 3. Changing it to limit h tending to 0, you will write in modulus -3 minus h plus 3. Putting the value of h as 0, we get it as 6 only. Let us check the RHL, where you write -3 plus. For greater than -3, the value of the function is minus of 2x. So now changing it to limit h tending to 0, -2 minus 3 plus h, putting h as equal to 0, we get 6 is the answer. You see all the three things, LHL, RHL and value of the function are equal. Hence this is a continuous function at x equals -3. Now when x lies between -3 and 3, you see the function is minus of 2x. So it is a polynomial function, will be continuous. In fourth case, you have to do as I have done in case 2. You will check LHL, RHL and the value of the function at 3. In fifth case, you see it is a polynomial function for greater than 3, and hence it will be a continuous function for all real values of x that are greater than 3. This is how you check the continuity of the functions or point of discontinuities of the function. Let us move to the next topic now. The next topic is differentiability. In differentiability, I told you the meaning of how to check differentiability, or what do we mean when we say a function is differentiable. When we say a function is differentiable, it means at every point of the curve there exists a unique tangent, right? So let us just take one example. Suppose I am taking this. F of x is modulus of x minus 1. So you just to see, you can break it in two parts. F of x will give you x minus 1 when x is greater than equal to 1, and 1 minus x when x is less than 1, because it will become negative then. So when we solve it, LHD formula, you know, limit h tending to 0, f of c minus h. C here is 1. So you'll write 1 minus h minus f of c, which is f of 1 divided by minus h. For RHD, we will write limit h tending to 0, f of 1 plus h minus f of 1 divided by h. Now be careful here, when you solve f of 1 minus h, this value is to be placed in which function? This is LHD, that means less than 1. So this function you have to take for LHD, right? And for RHD you have to take this function, the first one, which is x minus 1. So when you solve it, you are going to get different values for LHD and different value for RHD. Hence you will find that they are not differentiable at x equals 1. Also we see, I can show you on a graph. So at 1 it will start, right? So the graph will be like this. It will have a corner point. Many lines that can be drawn on this, just see carefully, right? So it is not a differentiable function. Let us go to the next concept, which is derivatives. In derivative, first of all, we did chain rule. In chain rule, you know what do we do? Chain rule, suppose, let us understand it with the help of an example. Function is given as y equals 5 cos of x cube. So first of all, you are going to do for, we will write dy by dx, which is differentiating y with respect to x, 5 as it is. Differentiation of cos of x cube is minus sine of x cube. Then we will do for x cube, which is 3x square. This is how we do and apply chain rule, because we know cos of x cube is not just function, it is composition of two functions. So now let us go to the next concept. After chain rule, we have higher order derivatives. That means the second order derivative in the exercise was asked to be find out. Equals log of x. Let us find differentiation of y with respect to x. We get differentiation of log x will be 1 by x. Now again you have to differentiate it. This is known as higher order derivative. That means I am finding the second order derivative. So it will be minus 1 upon x square, because it can be written as x to the power minus 1. So second order derivative for y is minus 1 upon x square. Now we can find the third order derivative as well. This is how we solve it, right? Whatever we get the value for dy by dx, we differentiate it then, right? Then in the next exercise, we had logarithmic and exponential differentiation. You know, differentiation of e to the power x is e to the power x only, right? So suppose you have e to the power sine x. Suppose we have to differentiate it. So when we differentiate it, we get e to the power sine x, and then we do for sine x, we get cos of x. So this is how we solve it. Logarithmic differentiation is really very important, and it is used where we have function to the power function. Suppose I say we have x to the power x, or x to the power log x, or we have log x to the power cos x. Like function to the power function is there, variable to the power variable is there, variable to the power function is there, or function to the power variable is there. So suppose I am solving this one, log of x and cos of x. So if y is equal to log of x whole power as cos of x, taking log on both the sides, you will get log y equals cos x into log of log x. Now considering this as u, that means cos x, and considering this as v, we can apply product rule and solve the differentiation. This is how we find dy by dx. If we have function to the power function, variable to the power variable, or variable to the power function, function to the power variable, we have to just take log on both the sides of the equation. Now comes parametric differentiation, in which x and y are not given directly in terms of each other. Instead, they are related through a parameter. So in parametric, suppose I take the example, x is given as cos of t and y is given as tan t. So you see, x is in terms of t, y is also in terms of t. So we will first get dx by dt. Differentiation of cos t will be minus of sin t. Dy by dt will be, that means we are differentiating with respect to t. Tan t differentiation will be secant square t. To find dy by dx, we have to do dy by dt divided by dy by dx by dt. Correct. So we will get secant square t divided by minus of sin t. Right, we can just now convert it into cos and can write the answer, or also we can leave the answer here as minus secant square t into cosecant t. Like this also we can write our answer. So this is how you express without eliminating the parameter t. We have actually solved the function and find out dy by dx. This is how we do parametric differentiation. After this there are theorems, which is the last exercise, where there were two theorems. The first one was Rolle's theorem. There were three conditions to check the applicability of Rolle's theorem. The first one is your function is continuous in the given interval. Suppose it is a comma b. Second condition is the function is differentiable in the open interval a comma b. Third condition, f of a should be equal to f of b. If these three conditions are satisfied, we say Rolle's theorem is applicable to that function, and then we write f dash c equals 0. That means first order derivative of the function, where we replace x with c, and from here we calculate c, which belongs to a comma b only. C will be any value between a and b. Right, this is how we solve it. In Lagrange's theorem, we had two conditions to be satisfied. Right, the first one was continuity of the function. So the function should be continuous in the interval a comma b. The function should be differentiable, right, in a comma b. If these two conditions are satisfied, we write f dash c equals f of b minus f of a divided by b minus a, where a and b are the values in the interval given in the question. From here also we find c, which belongs to a comma b. Clear? So this is how you are going to solve Rolle's theorem and Lagrange's theorem. So for homework, you are going to revise the complete chapter and go through the complete summary which is given in the NCERT, all the theorems. We have already done in other lectures everything with examples. Also we have discussed all the exercise questions. So you just have to revise the chapter, solve the questions, do miscellaneous exercise carefully, and prepare for test. So all the best. Do well in your test.